All right. So 17.2 line integral. So we need to go back and understand how we get piecewise smooth curves. That means we need to learn how to, well, we'll need to review how to parameterize every single kind of curve, right? Remember parametric functions? Well, parameterizing lines. Come on, guys. You know how to parameterize lines. You have an initial point and a direction vector. Easy. Parameterizing circles, cosines and sines. All right. You know how to parameterize those. Parameterizing other functions. Well, just give the independent variable, the t parameter, and substitute it in the function that gives you the set of parametric equations. We're going to do a lot of this again. Okay. So number one. Why do we want piecewise smooth curves? Because, for instance, what if you have this curve, so to speak? Okay, let's see. Um, so this line, and then what else do you have? Some sort of a circle, and then another line, right? And then like a sine wave, and then another line right here, Do you see this? Even though this function is continuous, but it's not piecewise. It's not smooth because of these sharp corners right here. And well, so that's going to describe the trajectory of an object traveling through this curve. As a piecewise function, where each piece will be cut by these sharp corners here. All right. Well, let me get rid of this. Okay, so let's parameterize. Let's parameterize a line segment, the line segment that goes between the point 251 and to the point 320. I mean, what do we need? An initial point. So this is x naught, y naught, z naught. That's what we put in our vector value function. And we also need the direction vector. Let me call this point A and B. All right. So the vector AB will be 3 minus 2, that equals to 1, 2 minus 5, negative 3, 0 minus 1, negative 1. All right, so the parametric equations are going to be given by r of t equals, okay, x, y, z equals, okay, the first terms of each equation, it's going to be the coordinates of the initial point, that is 2, 5, 1, plus minus in this case, and plus. Okay, plus 1t, which is t, minus 3t, and plus, actually, negative 1t minus t. So this is how we parameterize a line. That's basically week 1 material, right? Which we use in some of the subsequent weeks as well. So we're bringing it back, we're reviewing this, because we're going to do a lot of these parameterizations in this section, and pretty much the rest of the chapter. All right? Okay, let's parameterize a circle of radius 5 centered at the origin. Well, I mean, how do we parameterize a circle? Well, first of all, let's write the equation. X squared plus y squared equals to 25. So, r of t, in parametric form, x equals something, y equals something. How do we parameterize a circle? Square root. Well, I mean in parametric form, not really solving for y. Mm-hmm. This is Calc 2 material, by the way. And we have done, of course, a bunch of parameterizations of circles throughout this semester as well. I mean, this summer course, right? Any ideas?
Cosine t squared and sine t squared?
T squared? Well, not squared. Okay, there's a cosine involved. All right, but I would be missing something. The radius. Where do we put the radius? Okay, so that would be 5 and 5. Is this the only way to parameterize a circle? That's not the only way. Recall that the parameterization of a function is not unique. So, for instance, or we can also express it like x and y equals 5 sine t, 5 cosine t. What would be the difference between these two? What's the difference? It's the orientation, right? The orientation. What about the orientation of this circle? Clockwise or counterclockwise? Counterclockwise, right? We need to indicate the direction. What about this other circle? Well, of course, right? Clockwise, right? There's not much to say here. All right. Okay, what about curves in space? Okay, let's have a look at, at this curve in space, and notice how this is a piecewise smooth, because, well, it's a smooth curve from the point 200 to the point 345. That's why it's called C1. And it's also smooth from the point 345 to the point 340. So that's why we have to express this as a piecewise function. And I'm going to go back and use the vector notation, for instance, in this case. Well, number one, we need to find out the direction vector for these between these 2 points. That is terminal minus initial, 3 minus 2. Okay, let me call this vector, well, let me just write down the vector. Okay, so the related vector, that is 3 minus 2, that's 1, 4 minus 0, that's 4, 5 minus 0, that's 5. And then the direction vector between these 2 points, 3 minus 3 is 0, 4 minus 4 is 0, 0 minus 5, that's a negative 5. 0, 0, negative 5. Alright, so let's write a piecewise function that describes the trajectory of an object going through C1 and then C2. Okay, so R of t will be C1 first of all. So C1, what do we have for C1? Number one, okay, the initial point for this curve, that even though it's a line, that's technically a curve. So that's going to be 2 plus 1t, that's just t, comma 0. I'm not going to write the 0, 4t, and another 0. I'm not going to write that 0. That's going to be 5t. All right. And recall that whenever we parameterize curves, or when we parameterize lines using terminal and initial of a given segment, this always tells us that t varies between 0 and 1. All right, unless we needed to evaluate the function in a different, or rather to represent the vector value function in a different way. But typically, the easiest way and the most practical way to parameterize lines is going to be using the initial and the terminal, because the initial time is 0 and the terminal time will be 1. And guys, we'd better do it this way, because we're going to work integrals with these functions using these limits. And what's better than integrating when one of the limits of integration is 0, right? Yep. That's one of those dream come true, right? So let's see. C2. So C2, okay, initial, careful, the initial point is 3, 4, 5. So 3, 4, 5. Okay, plus 0 times t, well, there's nothing to multiply here, plus 0t. Okay, that's just 3. 0 times t, another 0 here, and 5, or rather 5 minus 5t. All right, that's how we parameterize this. Okay, that's from 0 to 1. All right. Well, I mean, you might argue, well, shouldn't this be t equals 0, t equals 1, maybe t equals to 2? No. Don't do t equals 2, 3, or 4 or 5. No, just look at every trajectory, or at every piece as one part, I mean, from 0 to 1, game over. Next C, 0 to 1, game over. If you had a C3, 0 to 1, C4, 0 to 1, C5, 0 to 1. Okay? So don't make this complicated, because again, you are going to wish to have all these limits of integration all the time, 0 to 1. You'll see when we apply this to the integrals. All right. Finally, let's get to the line integrals. Actually, we're going to discuss 3 types of line integrals. Number 1, this is type 1. Type 1 line integrals. All right? So, but again, what is a line integral anyway? So remember that what was that? That pop quiz we gave. What was that? Yesterday, or it was yesterday, right? Okay. Let's have a look at the different integrals we have studied. Okay, number 1, we have studied integrals over an interval. That is, the integral from a to b, that's over the interval a, b, of some function f of x dx, all right? I mean, that f of x function can be just a number, 1, or even 0, you know? So, but still, regardless of that, we are integrating over the interval a to b. And we can have a function at the top that doesn't matter, where this is technically the delta x, which is the same as saying our dx, all right? Then we made it more interesting in this class, and we integrated over a plane region, all right? So that means that's the double integral of some function f of x y dA, where in this case we have some plane region. But what did we do right here? Didn't we partition this region into infinitely many squares whose length, what is that? Delta x by delta y. In a similar way that we did a Riemann sum for an integral over an interval to get the area under the curves. So in this case, we partition that interval into infinitely many of those differentials, right? Like this partition right here, delta x. But that was for a length, because we were integrating over an interval, over a length. Now we're integrating over a plane region. That's the two-dimensional one. Then let's see. Integrals over a solid region. That is a triple integral over some region Q or D, that doesn't matter, of some function f of x, y, z, dv, where that triple integral may have just a 1 that represents a volume, or that integral may have an f of x, y, z that represents mass, all right? The mass of a solid, of the solid given by this solid region. Okay, how did we do this differential, so to speak? Well, in this case, rather than partitioning an interval over with infinitely many lengths, delta x, or rather than partitioning a plane region with infinitely many of these square partitions, delta x by delta y, this time we partition a solid into infinitely many of these rectangular boxes. That is delta x by delta y by delta z, right? And then we'll find the volume of that partition, and then add infinitely many of those partitions, preferably the smallest, delta x, delta y, delta z, the better. The smallest, the better, because that will give us a more refined result. In a similar way that we got these rectangles with the delta x length of or base of the rectangle as tiny as possible, to give space to more rectangles, infinitely many rectangles, to get a more refined. I mean, you guys know this story about Riemann, right? So all we did is put a 2D glasses and put 3D glasses to it, right? To describe double and triple integrals respectively. Okay, guys. Let's have a look at this. What is that? What's that? If you look at that, what does that represent? Hmm? It's a plane region, right? Number one. It's a plane region. Okay. What else? Mm-hmm. I heard something, and that's on this side. Okay. What else did you see? Mm-hmm. Yes, it's a plane region. That's correct. Uh-huh. What did you see? Whatever it is, just name it. Just name it. Whatever you have in mind.
It's from an interval from like 1.5 to like 5.5 looks like.
From, I believe it's from 1 to, yeah, it's for 1 to 7. But what else do we see? So that's the interval 1 to 7. It looks like a diagonal line, right? That line right here. This one, this diagonal line, right? What else do we see?
It's like two geometric shapes.
It's two geometric shapes. A square and a triangle. Okay, what else?
Looks like a projection of like a trapezoid, at least on like the X.
It's a trapezoid on the XC plane. Okay, yes, all right. Why not? That sounds good. What else? Does that remind you of something you did, maybe Calc 1? That's my hint. There's something you need to get out you need to get of this. Does that remind you of something from Calc 1? If so, what is that? So yes, we have that diagonal line over the interval 1 to 7. What else? It's there. Curve. It's the area under the curve, this diagonal line, and yes, within the interval 1 to 7. I mean, that's Calc 1, right? So that's what this integral does, right? Remember, okay, let me go back to the notes right here. That's what this integral does. Find the area under the curve within two values a and b, all right? But what about this line integral? What does that do? That's interesting, because what if I rotate this image and make it look 3D? All right? So this line integral, this type 1 line integral, would give us the area under this curve in space, or potentially the curve in the plane as well. But I think the space example looks better, because to make a distinction between the integral you learn in Calc 1 and that one that we're learning in this Calc 3 course. So this is really it's still area, but not under the curve, but rather the area of defense created by this, or projected by this curve in space. So that's what we're going to calculate here. All right. Well, let's have a look. Let's go back to the notes here, and we have another representation of what the scalar line integral is about. So, and in a similar way, we partition a plane region, a curve, into infinitely many rectangles. Well, we're going to do the same here. So, do you see all these rectangles? Again, very similar to Riemann's idea from Calculus 1, all right? However, these are rectangles in space under the curve, creating a fence or a curtain here. Okay? Now, again, I'm going to do the same. I'm going to take, what is that? One representative rectangle. Okay? One representative rectangle. So, but the thing here is, how am I going to create the Riemann sum that calculates the area under the curve, under the curve in space? Well, number one, I would use delta x, right? Because that's the length of the rectangle. But no, in this case, we already have x for the x dimension, the y dimension, and the z dimension. So I need a different element. Remember the letter we used to describe arc length? What was the letter we used to describe arc length? Remember? S. So I'm going to use delta S right here, right? And what is the height of the function? Well, whatever f of x, y is, right? F of x, y. So because right here, every point I'm plotting here, it's going to have a height z, right? How do we get that height z? Don't we get it by evaluating the x and the y coordinate? That gives us the height of the function, right? In a similar way that in the 2D version, you get the height of the function by evaluating that function at the given x value, right? Now let's put our 3D glasses and see it in 3D this time, okay? So, partition, again, area, come on. Area equals length times width. I mean, basic geometry. What's the length? Delta S. What's the width, or what's the height or the width? F of x, y. All right? Well, that's the area of only one of those rectangles in space. So, if I wanted the entire area from point A to point B, for instance, I would need to add n of this. You know, that is sum f of x sub I, y sub I, times delta S. The delta S doesn't come with an I subscript because it's the same length for every single rectangle. Okay, you know the whole story about Riemann. How do we get the actual result? Well, this is an approximate result if you partition this image into what? Say 5 rectangles, 7 rectangles. That's an inaccurate result. You want the accurate result? Find the limit as n approaches infinity. All right? But of course, you're not going to compute infinite areas. That's why you have the limit idea. That's why you have Riemann sums. From I equals 1 to n of f of x sub I, y sub I, delta S. That's equal to the value of the area between A and B. And guys, it looks like this. Hold on. Now look at the limits of the integration. Look at the form of this integral. It looks a little weird. It doesn't have limits a to b like the regular integrals we learned back in calculus 1, or a to b, c to d like the double integrals, or a to b, c to d, e to f like a triple integral. Notice the subscript below the integral symbol. Well, this is to describe what is the path or the trajectory over we're integrating. So what are we going to do? We're going to find the area under the fence along that curve C. Okay? So let's see. Let's have a look at one example to see this in action. And by the way, notice the variable, notice the parameter s. Remember, that's the arc length parameter. Remember when we were given a vector valued function and we were asked, determine whether this vector valued function describes the arc length parameter. You would take the derivative, find the magnitude, and if you get a 1, then you can simply change to s. But well, we will discuss about that. I mean, look at this. Cosine s, sine s. Take the derivative, that's going to give it, its magnitude is going to be 1. I mean, just look at that. That's a unit circle. All right? From 0 to 2 pi. What are we going to do here to evaluate this integral? So the integral of x squared plus 2y squared ds, okay, that's along the trajectory C. And this is just going to be a pretty basic substitution. Check this out. So what we will do here is every instance of x in your integrand, replace it with your x component of the vector valued function. While every instance of y, replace it with the y component of the vector valued function. And the limits of integration, I think they're pretty obvious. They're there, right? Just for us ready to compute. Okay, so that'll be the integral. So no longer in terms of x and y, but rather in terms of s from 0 to 2 pi. And that equals, what's that? X squared plus 2y squared, where x equals cosine s squared plus 2 times sine squared s ds. Okay? That's pretty easy to integrate. Well, I would need a little trick here to simplify this integrand, because I can't integrate cosine squared in one shot. I can't integrate 2 sine squared in one shot either. I would need to use the power reducing formulas for cosine and for both sine and cosine. But I don't want to do two. I don't want to use both at the same time. However, how about break up this 2 sine squared s as cosine squared s plus sine squared s plus another sine squared s ds. Do you guys agree with me that 2 sine squared equals sine squared plus sine squared? And check this out. What is cosine squared plus sine squared? Come on, right? Right? That equals to 1. Okay. So that means the integral from 0 to 2 pi of 1 plus sine squared of s ds. Alright? And well, in this case, yes, it's better to use this power reduction formula only once rather than twice. Alright? So I will replace this with integral from 0 to 2 pi. The power reduction formula for sine, that's 1 plus 1/2 1 minus cosine 2s in this case, right? So let me highlight so you can see how did that go. Okay, so I'm replacing this with its corresponding trig identity. And this one is easy to integrate as opposed to the square one. Okay, so let's distribute, that's ds. That equals the integral from 0 to 2 pi of 1 plus 1/2 minus 1/2 cosine 2s ds. The rest of the problem is just a calculus 1 problem, right? 1 plus 1/2, is that 3/2? That's 3/2. Whoops. The integral of 3/2 minus 1/2 cosine 2s ds from 0 to 2 pi. Okay? And what's next? Yes. So that's the integral of 3/2, which is 3/2 s minus 1/2 times the integral of cosine, which is sine 2s, but because of these 2s, there's another 1/2 involved. And we'd better integrate this evaluate between 0 and 2 pi. That's going to give us 3/2 s minus 1/4 sine 2s from 0 to 2 pi. Okay, a lot of cancellations, nice cancellations will occur here, you'll see. Okay, so 3/2 times 2 pi minus 1/4 sine of 2 times 2 pi minus, did you guys agree that that substituting 0 to the two terms here will give us 0? I mean 3/2 s 3/2 s at 0 is 0. Sine of 2 times 0, which is 0, that's 0, right? Minus big 0. Sine of 4 pi, that's 0. Divide this out, 3 pi. So that's the value, right? Okay. So what are we finding here? We're finding the area of the fence for this surface that intersects with the unit circle, right? That's what we're calculating here, right? Okay.